Hi everyone, my name is Thibaut. I'm engineer at Crypto Garage working on peer-to-peer derivatives projects, which consists mainly on working with like the discrete log contract protocol. And Ichiro, you want to introduce yourself?
Yep. Hi, I'm Ichiro. I'm working as a researcher at Crypto Garage. I'm focusing on Bitcoin technology and also thinking about the financial products based on the discrete log contracts.
Yeah, so with Ichiro, lately we've been working quite a lot on moving from like a discrete log contract protocol punishment-based DLC protocol to version of the protocol using adapter signatures. And we learned a lot of things. We thought it was really interesting, and today we wanted to share with you, like, what we've learned, and hopefully this can inspire other people to use adapter signatures in other contexts, and also get other people to get an understanding of how like the DLC protocol with adapter signatures work. So first of all, I'm going to recall a bit the original DLC protocol, and then how the adapter signature version differs. And I think hopefully that will really show like the power of adapter signature. So is going to explain a bit more like the mathematical details of how adapter signatures work, both like when we are using Schnorr signatures or when we are using ECDSA. And finally, I'll do some demonstration when using, like coding demonstration in Rust on, how to actually use adapter signatures in code. And finally, I'll demonstrate our peer-to-peer derivatives application where you can now do some DLC with some counterparties. And we just updated to use adapter signatures. Right, so just to recall a little bit the DLC concept, for example, if you have Alice and Bob, and Alice goes to Bob and says, hey, I bet you that, Trump is going to win the US elections. And Bob agrees and wants to do a DLC. So what they're going to do is that they're going to find a so-called oracle, which is like a third-party entity that is going to attest to the outcome of the event. And using this oracle, they're going to be able to, create like a contract or Bitcoin transactions that make up the contract. And so they're both going to put one BTC. And when the event has occurred, so after the result of the US election, the oracle is going to release an attestation over the outcome, saying, for example, Trump or Biden has won the election. So if Trump wins in that case, using this attestation, Alice is going to be able to recover 2 BTC, her 1 BTC that she put originally, plus the 1 BTC that she got from Bob. So some nice properties about DLC is privacy. So actually only the 2 parties that enter into the contract need to be aware of the contract. And in particular, the oracle doesn't need to know about the contract, which is quite nice and quite different compared to some other decentralized finance protocol where there is a lot of information on chain, which is visible by everybody. And of course, the fact that there is no extra information on chain is also good for scalability, since again, the only thing that appears on chain is actually Bitcoin transactions, and of course the signatures that are required to unlock the outputs. So DLC is also trust minimized. Of course, you need to trust the oracle, but again, because the oracle doesn't know about the contract, then there is less room for collusion between the oracle and the parties. And it's also possible, even though that's not something that is currently well supported, to use multiple oracles. So that if you pick maybe 2, 3, 5 oracles, like the chances of all of them colluding with your counterparty decreases quite significantly. Also, of course, the 2 parties that don't need to trust each other at any time in the protocol, they are able to either recover their funds or be guaranteed that the event. And if the oracle were to fail, like not release actually an attestation, then both parties can be sure that they'll be able to be refunded. And that's just my my view on the thing. But I think like basically the trick in DLC and what makes it really interesting is like this way of let's say reinterpreting a bit how Schnorr signatures work, and we'll see that a bit more with Ichiro a bit later. But basically, how it works is that we have the Oracle is going to release some information ahead of time, and this information is basically a public key, and then like elliptic curve points, so also kind of like similar to a public key. And using these two elements, the parties, they are able to, and these two elements as well as the outcomes for the possible outcomes for the event, so they're going to be able to pre-compute some so-called signature points, which are quite similar to public keys in how they are represented. And then once the Oracle releases the signature, actually this signature is basically the private key. That's a bit abusing the term, but it's basically like the pre-image of the signature point that was computed before. All right, so now we're going to see, like we're going to recall like the original DLC protocol, punishment-based, punishment similar to how the Lightning Networks is currently implemented. So here we can, we have an overview of all the transactions that are involved into the punishment-based DLC protocol. So on the left here, we have the front transaction, which is pretty much similar to the front transaction in the Lightning Network. Both parties input some funds, and these funds get logged into 2 out of 2 outputs, multi-sig output. In the middle here, we have 2 sets of so-called contract execution transactions. And these CETs, there is one for each of the possible outcome of the event. So for example, for the presidential election, in that case, we probably have 2 or maybe a bit more if you have more candidates. But yeah, so for each of the outcome, you have like a one contract execution transaction, and like the outputs here, they correspond to the payouts that were decided by the 2 parties originally. And so Alice's contract execution transactions, the payout for her payout is actually logged with a specific script, which enables her to recover these funds only if she actually knows like this pre-image of the signature point. But her cities, they pay directly to Bob. And on the other side is the opposite. Bob is only able to unlock his payout using the signature from the Oracle, but Alice can get paid directly. And that's the refund, which is time locked. So to sometimes, quite after the maturity of the contract, if the Oracle were to fail to release a signature. And yeah, so and here that's why it's a punishment model, because if Alice actually were to broadcast this CT, for example, without having the signature from the Oracle, she wouldn't be able to unlock this output here. And after some time, Bob would be allowed to actually unlock this, and then would actually get all the funds. So again, this is quite similar to how the Lightning Network works at the moment. So the setup, how it works is like, so Alice would first sign Bob's CETs and the refund transaction. Then Bob would sign Alice CETs and the refund transaction. So now both parties are guaranteed that they can either get refunded or use like one of the CET. And so they can now safely sign the fund transaction because, again, like they're able to either recover their funds or exercise like or get like the payout that corresponds to the event outcome. And at least she can sign finally and broadcast the fund transaction. However, because as we saw here, using this CT is a bit impractical. And if you actually want to recover your funds at the end, you actually need to have this closing transaction here. So in total, you would need like 1, 2, 3 transactions to really close the contract. So this is a bit impractical. So if the parties agree, since anyway, there is no other possibilities and to actually get this payout once the oracle releases the attestation. They can agree to create a so-called mutual closing transaction, which this is just like the payouts that correspond to the event outcome. And so they can cooperate and create this transaction and broadcast it so that they can save a bit on fees, and also it's a bit more private because there is no like special script here involved. And so on chain, like the fingerprint is maybe the same as it would be for the Lightning Network, or even like just a multi-sig 2 out of 2. But if they don't cooperate, then of course Alice can just use her CET to get a signature. And if she misbehaves by sending like the wrong CET, then Bob will just have to wait until this time lock expires, and he will be able to send the punishment transaction and recover all of the funds. So now we're going to see how things change when we use adapter signatures, actually. And this is now the set of transactions that are involved into the adapter-based DLC protocol. And as you can see, it's like much simpler. And so now we're going to try to understand how come it's possible to simplify so much. And that's thanks to adapter signatures. So just to give a high-level view of what are adapter signatures, I like this definition that was given by Lloyd Fournier in the paper he wrote about this, the notion of verifiably encrypted signatures. So basically, an adapter signature is an encrypted signature and you can verify basically that it is an encrypted signature for which if you get like the private key to decrypt it, you're guaranteed that it's a signature over a message. So basically, you take a message, you sign it with your private key, then maybe you encrypt it with a public key, and you get an adapter signature. But here at that point, even without knowing the private key here, you can verify that this adapter signature encrypts a signature using this public key that corresponds to the private key here. And you can be guaranteed that once you get this private key here, you will decrypt it to the signature that was created here. So again, you have a message, you sign it, then you encrypt this signature, and your counterparty or anybody else can verify that this is actually this adapter signature is actually the encryption of this signature here. And so that if someone gives you this private key, then you can be guaranteed you're going to recover exactly this. And now we're going to see how that comes into application into DLC. So in DLC, basically, like the message in general is like some transaction information, like that like what you sign is usually like to enable unlocking some UTXO, and that involves like part of the spending transaction and UTXO. And so you sign this, so you get a signature, and here you're going to encrypt this signature using the Oracle SIG point. That, if you recall, you can compute using the info outcomes. So basically, here you're going to create like as many adapter signatures as you have like possible outcome. So once you get this adapter signature, your counterparty can verify that this adapter signature actually encrypts a signature that will enable him to unlock some UTXO. And then once the Oracle releases the signature, this adapter signature can be decrypted to a signature that will enable unlocking some funds. So if we look at how things go step by step, first of all, Alice is going to give Bob an adapter signature for CET, for the CETs. And again, here you can see like there is only one set of CETs now. Like it's exactly the same both for Alice and Bob. And a regular signature for the refund, because anyway it's time locked, so it doesn't really matter. So yeah, here the oracle like gives like his public key and point he commits to, and Alice is able to compute like this signature points, and she's going to encrypt her signatures for the CETs using each of the possible outcome. So we have one CET per possible outcome, and so we have one adapter signature per possible outcome, which is encrypted using a different possible seed point from the oracle. So then Bob is going to give also some adapter signatures for the CETs, and he's going to sign the refund transaction as well. And because he has, of course, he needs to verify the adapter signatures from Alice. And if he can verify properly, then he can also like sign the front transaction, because he's guaranteed that when the oracle releases his signature, then he's going to be able to unlock one of the CET, or if the oracle fails, he's going to be able to use the refund transaction. And finally, Alice can also sign the front transaction and broadcast it. So now the oracle, at the time where the oracle releases a signature, Alice, for example, can take like one of the adapter signature from Bob, which correspond to the outcome that was released by the oracle, and then Alice is going to be able to decrypt this signature, and she's going to be able to broadcast it, and it gets included in the blockchain, and directly Alice and Bob can get their payouts. So if we look like, if we compare with the previous punishment-based version, not having a punishment mechanism is actually, of course, really nice, because it means, you don't have risk of, maybe broadcasting. So, it was maybe not intentional. You have only a single set of CETs, so in terms of implementation, is definitely simpler. Like in any case, it's more private than the previous version, because you don't, the CETs they don't include any special script. And especially if you use Schnorr signature, actually you can even have something that looks like just not even like a 2 out of 2. It's just like very simple regular signature. And something that is very, very nice is like, so in the previous example, we saw that at the end, the two parties could together create a mutual closing transaction to make things simpler and more efficient. But that, of course, requires some communication. But in that case, there is no need for that. They can just, unilaterally close the contract, and it's exactly the same. All right, so that's it for me for now, and I'm gonna leave Ichiro explain a bit more the mathematical details.
Can you see my screen?
Yes.
Okay, thank you. Before talking about the mathematical theory of adapter signature, first I will talk about the history of adapter signatures. And there are two types of adapter signatures. One is Schnorr-based adapter signatures, and the other is ECDSA-based adapter signatures. And now Bitcoin uses ECDSA signatures. First, as 2017, script was proposed, that is using Schnorr-based adapter signatures. And then secure key aggregation for scripts that is called MuSig was published as 2018. And then each day-based adapter signature using homomorphic encryption was proposed at 2018. With this protocol, we can implement right now because it is based on ECDSA signatures. And then adapter-based layer 2 solution was proposed. This can be used in the Lightning Network in the future. And last year, 2019, ECDSA-based adapter signature that doesn't use a homomorphic encryption was proposed. this protocol is using OP check multisig. So this is called semi-scripted scripts. And now DLC is using this protocol. Now today I will talk about the Schnorr-based adapter signature described in this number 1, and ECDSA-based signature that is using OP check multisig that is described in this number 5. Plus, I will talk about Schnorr signatures. Schnorr signatures is calculated in this formula. Signer first creates a small r, that is random number, and creates a random point, large R, that is equal to a small rg. By using it, creates a signature in this formula. Verification is described in this formula. And of course, verification is possible without using private information, like a small p and small r. And this linear equation in signature creation is a key point, because this linear equation enables us to create multi-party signatures by adding signatures together. And this is the party Schnorr signatures. Each party creates a small r and large R, and then they create a common public keys, large P, and common random point, large R, by using a multisig. And then by using these common value, each party create a signature in this formula and add them together. Yep. And verification is possible without using private information. Next, I will talk about Schnorr-based adapter signatures. Signer creates a small t and large T in addition to a smaller and small and large R. Small t is called tweak number and large T is tweak point. And by introducing large T to the adapter signature calculation, signer creates adapter signatures. Yeah, this introduction is called tweak. And the verification is described in this formula. And by adding T to the adapter signature S dash, signature is completed. This is two-party Schnorr-based adapter signatures. Each party creates a small r and large R and agree on the common public key and random point by using a multisig. In addition to large P and large R, they create a large T that is a tweak point equal to a small tg. By using this common value, each party creates a signatures and add them together. This signature calculation is a linear equation, so we can simply add these two signatures together. And by using a small t, adding a small t to adapter signatures, signature is completed. And this is about the Schnorr-based adapter DLC. It is almost the same as the previous slide. Only the point different from the previous slide is creating a large T from Oracle information. And at the maturity time, Oracle publishes a small t. And by using small t, each party decrypts the signatures and signature is completed. This large T is called sigpub in the Thibaut slide. and small t is called sig private in the Thibaut slide. Yeah. Next, ECDSA signatures. ECDSA signature is created in this formula. First, signer creates a small r and large R, then calculates the signatures in this formula. This equation includes r to the first minus power, so that prevents us to create the multi-party signature by simply adding them together, because it is not linear equation. So this is different point from Shuno signatures. And verification is also possible without using a private information and described in this formula. Next, ECDSA based adapter signatures. In addition to small r and large R, signer creates a small t and large t, that is tweak number and tweak point, and also creates another random point r dash. By using this information, signer creates a signatures in this formula. The point is using a small t, multiplying t to the first minus power to the adapter signatures. Signer decrypts the signatures, and the signature is completed. For using this R dash, we also need DLEQ. This is this discrete logarithm equalities, but I don't mention about it the detail. If you want to know about the DLEQ, please check our blog. And this is two-party ECDSA based adapter signatures with OP check multi-sig. Because this protocol is using OP check multi-sig, so each party don't need to create a small p and a small r by using music. So each party just need to create a large t that is equal to a small tg. And by using a large t, each party creates a r dash and creates a signature in this formula. And by using a small t, each signature can be decrypted. And this is ECDS based adapter DLC with OP check multi-sig. That is, this is the protocol that Thibaut explained. And the protocol is almost the same as a previous slide. And the different point is each party creates a large T from Oracle information that is called sigpub. And then they create the signatures, they create a transaction. And at the maturity time, Oracle publishes sig private, this is small t. And by using a small t, each party decrypts the counterparty's signatures, and signature is completed. So discrete law contracts can be settled. Yeah. If you want to know about the more mathematical detail, please check our blog. Okay. I will pass the baton to Thibaut.
Yeah, thanks, Ichiro. All right, so now I'm going to discuss a bit more practical side of things. First of all, I wanted to mention like where at the moment you can find implementation of ECDSA adapter signatures. So the three first three first libraries I'm maintaining. One in Rust is the fork of the Rust Sec56K1 binding for Rust. We have also a version in C++ and in JavaScript, which is like just a JavaScript version is just a binding for the C++ version actually. So these three are based on branch of sec56k1 C library that was made by Nadav from SureBit and Jonasnik from Blockstream. SureBit is also maintaining Bitcoin S, and there is an implementation of ECDSA adapter signature in Bitcoin S at the moment. Nicolas Dorier also has implemented that in C# in his NDLC tool, which is a tool to work with DLC in C#. And finally, Lloyd Fournier's he has this P256k fun library, and I could see he also has implemented ECDS adapter signatures there. So yeah, based on the what language you like, you have got some choices if you actually want to use currently ECDS adapter signatures. Now I'm gonna go through a small example. So if you're interested, you can find it here. It's highly possible that it's going to change over time because the APIs are not completely fixed, but hopefully it's not going to change that much that you can follow along. So yeah, here I already put some base code that is not so interesting to discuss. We just create an instance of the sec56k1 struct, some random number generator. Here we are gonna use a message to sign, but of course in practice that you would take some Bitcoin transaction information, some seed hash. This message will hash it because that's what you need to do if you want to sign it properly. Here we define two outcomes, head or tails, and again we hash them. We're going to generate like a public private key values. That's basically like that the Oracle needs to provide to the parties of the DLC in order for them to create the contracts, the Bitcoin transactions. So yeah, basically in practice, the Oracle would give like this public key and these R values, and you can see they are generated pretty much in the same way. And then so we have Alice and Bob, and again we are gonna create some public private key pair for each of them. So now the first thing we want to do here is create the signature points, if you remember. So the Oracle is going to give his public key and R value here, and then for each of the outcome, we're going to pre-compute some signature points. And we are going to do that by using a function that is called, I can find it, yeah, compute seed points. Yeah, so here basically we take the hash of the outcomes. So here we have two, head and tail, we hash them. So here we take that. And for each of them, we're going to compute a signature point using the R value that was given by the Oracle, as well as his public key. And that is going to give us like two signature points here. So this is what I called here like SOI. So here we have like we have SO1 and SO2, which correspond to head and tail. Now that we have these signature points, we are actually able to create some adapter signatures and the proofs that Ichiro quickly mentioned that we're not going to go into details here, but you can find more information in our blog. And so to do that here, we have the function adapter sign. So we take these 6 points, and for each of them, we're going to create an adapter signature. So Alice is going to use her private key to do that, and Bob is going to use his private key. So now we have like a set of adapter signatures for Alice and a set of adapter signatures for Bob. And this is a pair because it's not only an adapter signature, but also a proof. And then we have that for both Alice and Bob. So now, of course, each Alice and Bob, Alice is going to want to verify Bob's adapter signatures, and Bob is going to want to verify Alice's adapter signatures. So to verify this, we have a function for that, which is called adapter verify. So here we are going to take like these adapter pairs, and then we're going to zip that with like the signature points. So we take the hash of the message, like our original message, if you remember the word. And then this is going to be the adapter signature, Alice public key, the signature point, and the discrete like equivalence proof. And so if everything passes here, we know that the adapter signatures for Alice are actually valid. And we can do the same for Bob. So after this step, we can be sure that all the adapter signatures are actually correct. So that's what needs to happen at the setup time, basically. So once they have verified adapter signatures, they can sign the firm transaction and broadcast the firm transaction, but they know that they are going to be able to unlock one of the contract execution transactions once the Oracle releases the signature. So at contract maturity, the Oracle is going to be able, it's going to release the signature. So here we are going to create an additional signature here. In that case, for example, he's going to release a signature over the hash of the string head using his private key and the pre-ledger of the R value, which, the equation is written here, and that's what Ichiro explained before. And we're using the signature. A Schnorr signature is actually has two components. The first one is actually the R value, but so we already have it. We already use it for computing. We already know it, so we don't need it here. We just need to extract like the S. So we also have like a small function that I added here on Schnorr signatures to decompose and get like R value, S value. All right, then we can, for example, in that case, we're going to decrypt one of Alice's adaptive signature. So the first one, because that's the one that corresponds to the outcome that was signed by the Oracle. We just need to convert the secret key here. That's a bit of the details. It's just like the type system that requires this. And so we take, this is like the first adaptive signature of Alice. And yeah, we're going to adapt that with the S value. And that's going to give us the original signature that Alice created. And finally, to make sure that everything is working fine, we can just verify that the decrypted signature here is actually valid for our original message using Alice's public key and the decrypted signature. So, verify that everything is working fine by running this example. And I forgot to pre-compile, so it takes a little bit of time, but hopefully, everything passes. We don't have any failing, so everything is fine here. Maybe you can try, for example, if here, you can try it by yourself. You can try changing things, you can try, and you'll see things failing. But basically, that's how you do things. And for the other language I mentioned, the API should be pretty much similar. So you should be able to use that. All right, and finally, I'm going to give a small demonstration of our P2PDerivatives application. You can find it's open source, so you can find it on GitHub at this link. And if you want some, a bit more high-level information, you can see this Medium article, which links also some help or you can have to set things up. All right, so I have like two instances here running. So first, we're going to sign up Alice and Bob. So some username and password. Register. Right. then she needs to set up a wallet. So at the moment, you actually, in order to use the application, you need to have like Bitcoin Core instance ready. So on this setup, we're going to do the same for Bob. Just to log in. Right. Saying we're going to have to set up a wallet for him. Oh, sorry. Also, something we've added recently is the ability to connect to the Bitcoin Core RPC interface through Tor, and that's quite practical if you're using a BTC Pay server, because BTC Pay server allows that quite easily. All right, then we can connect. So we're going to create a new contract with Alice. Fee rates, so 25 BTC each, which is quite a lot, but you know, I've got some money this way in Bob. Says that, you know, if the price is between 12,000 and 13,000, then Bob is going to receive 50 BTC. And if the price is above 30,000, then Alice is going to receive the 50 BTC. So yeah, and yeah, it's just like, because we don't have so much time, we're just going to say that the contract is maturing in 2 minutes. And of course that works because we are on reg testing practice. That wouldn't be really good. So yeah, Alice received the contract. She can check, okay, well, yeah, that's quite a good contract for me. I'm happy to take it. So she's going to accept it. So she broadcasts the fund transaction, you know, so knows all the process of computing like adapter signatures, verifying them, all of that happens in the background, of course. And you know, Alice, once she's verified Bob's adapter signatures, she can sign a fund transaction, broadcast it, which is just what happened here. We're going to generate some block so that you know the contract is confirmed. Of course, I'm on reg test, so you know that you can do that. If you're using testnet, you need to wait a little bit and set some different times. And so yeah, you can just check, you know, that everything looks good. And normally, let's assume we should be able to have the contract closing. So I think that's 40. So we still have a couple of seconds to wait. Yeah. See, there's not a good timing. But yeah, otherwise the app is pretty simple. If you have, you know, if you have any difficulty using it, or if you find some bugs which you know happened before and unfortunately might happen again, please, you know, feel free to contact us. And or if you have any feedback, we are really happy to, you know, add new features that could be requested. So yeah, finally our contract is closed. We can check. In that case, actually, Alice made some profits, so Bob made some loss. That's how it works. And you know, you get like an overview of how the contract was. And yeah, yeah. Actually, something I forgot to show is that even if you know Bob was actually not online, Alice would have been able to close the contract by herself, again without having any difference, because the closing in the DLC adapter protocol is just, you know, unilateral in any case. I hope, you know, you've got some better understanding of adapter signatures, and in particular how they are used in the DLC protocol. And you know, hopefully that can inspire you to, you know, either use adapter signatures in other contexts or also to use DLC. There is several implementations available for ECDSA adapter signatures that, you know, can work with Bitcoin today. So that's really quite nice. And hopefully, and of course, like once we also get Schnorr signatures, things will be even better because we'll be able to have even more private DLCs and other protocol taking advantage of adapter signatures.